Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting area, the idea of less is more in the context of AI reasoning, specifically as it relates to a paper someone cleverly titled LIMO. It's about how perhaps focusing on simpler models, especially when informed by neuroscience, might actually get us further than just throwing more data and parameters at the problem. Might actually get us further than just throwing more data and parameters at the problem. So, who wants to kick us off with their initial thoughts?
I'm happy to jump in. Less is more is definitely an appealing concept, especially after seeing the resource drain of these massive language models. But I'm a little skeptical, to be honest. My initial reaction is, while simplicity is great, isn't complexity, or rather, sufficient complexity, necessary to capture the nuances of real-world reasoning? I mean, the brain itself is incredibly complex. Are we really going to outsmart evolution with a minimalist approach?
I see where you're coming from, but I think the point is that the current complexity might be misplaced. It's not about dumbing things down, but about finding the right kind of complexity. For example, neuro-symbolic AI, where you combine neural networks with symbolic reasoning, has been trying to address some of the limitations of pure deep learning for a while. Maybe the less is more is in the number of parameters, but the structure and the way the information is represented needs to be more sophisticated and right.
Exactly. I'm with Sarah on this one. It's about efficient complexity. Think about it. The brain is incredibly energy efficient. Deep learning is a brute force approach. It's like trying to build a bridge by just piling up rocks until they form an arch. A real engineer understands the principles of stress and strain and can build a much more elegant and stable bridge with far fewer materials. And I suspect the core principle we're missing, especially for reasoning, has something to do with how the brain handles spatiotemporal relationships, how it translates between different coordinate systems. Current models are terrible at that.
Spatiotemporal relationships. Elaborate on that, Donald. I'm not quite following how that ties into the less is more idea.
Okay, think about driving a car. You're constantly translating between your visual field, your sense of motion, the map in your head, and the physical controls of the car. That's multiple coordinate systems operating simultaneously. Deep learning struggles with that kind of translation. It can learn to associate images with steering wheel movements, but it doesn't understand the underlying geometry. A less is more approach would be to focus on the core algorithm that allows the brain to perform these coordinate transformations efficiently, rather than just throwing more data at a network until it memorizes a bunch of driving scenarios.
And that resonates with me quite a bit. It's almost like we are looking at the forest through a magnifying glass instead of the core components. That's kind of the crux of this whole discussion, right? I mean, the paper that sparked this conversation, LIMO, seems to imply that language models, despite their impressive abilities, still fall short when it comes to complex sequential optimization problems. That suggests a fundamental limitation in their architecture, maybe because they are data-hungry, brute force approaches. Do you think that's a fair assessment?
I see the point, but I also think we're maybe underestimating the power of scale. It's possible that these limitations are just a matter of not having enough data or not having the right architectures yet. Maybe we just need transformers that are even bigger and more complex to finally crack these problems. I mean, think about how far we've come in the last few years just by scaling up. It's been exponential.
But is that really reasoning or just sophisticated pattern matching? We can build these models that generate text that sounds coherent, but do they actually understand what they're saying? Do they have a model of the world that allows them to reason about cause and effect, to make inferences, to generalize to novel situations? I'm not convinced. That's why I think we need to go back to more symbolic approaches, where knowledge is explicitly represented and reasoning is performed through logical inference.
But symbolic AI has its own problems, right? It's brittle, it's hard to scale, and it struggles with uncertainty and noise. Neural networks are much better at dealing with messy, real-world data. Isn't the ideal solution some kind of hybrid approach that combines the strengths of both?
Yes, and that's what's exciting. You're hitting at exactly the right point. I'm intrigued by the potential of marrying symbolic processing with neural networks. It's not one or the other, but how can we make them work together? And how can we use neuroscience as a guide? The brain, after all, seems to integrate different modes of representation and processing seamlessly.
And that integration, I think, is where the spatiotemporal piece comes back in. Think about how the hippocampus works. It's essentially a spatial map, but it's also used to encode temporal sequences. It's a spatiotemporal coordinate system. If we can understand how the brain uses these kinds of representations to perform reasoning, we might be able to design AI systems that are much more efficient and robust than current deep learning models.
Okay, I'm starting to see the connection. So you're saying that the less is more isn't about just simplifying the architecture, but about identifying the right kind of representation, something that captures the essential structure of the problem and allows for efficient reasoning. Like, maybe we need to move beyond just vectors and matrices and start thinking about graphs or other more structured representations.
Exactly. And the less is more might also apply to the learning process itself. Instead of just throwing massive amounts of data at a network and hoping it learns something useful, we might need to provide more structured input, more guidance, more explicit constraints. Think about how children learn. They don't just passively absorb information. They actively explore and experiment and receive feedback from their environment.
And that active exploration and experimentation, it's almost like the brain is building its own internal models of the world, its own coordinate systems through interaction with the environment. And these models aren't just static representations. They're dynamic and adaptable, constantly being updated and refined.
Right. And the key, I think, is that the brain can translate between these different models. It can take information from one coordinate system and map it onto another. That's what allows us to reason about complex situations and make predictions about the future.
So, if we were to translate this into concrete research directions, what would that look like? Are we talking about new neural network architectures, new training algorithms, new kinds of data representations?
From my perspective, it's definitely about exploring new neuro-symbolic architectures. We need to find ways to seamlessly integrate symbolic reasoning with neural networks so that we can get the best of both worlds. One specific direction would be to look at how we can use symbolic representations to provide more explicit constraints on the learning process, guiding the network towards more interpretable and generalizable solutions. We also need better ways to evaluate these systems. Current benchmarks are often too superficial and don't really test for genuine reasoning abilities.
I think we need to focus on developing neural networks that can learn and manipulate different coordinate systems. That might involve incorporating explicit biases into the architecture, such as internal maps or attention mechanisms that allow the network to focus on relevant spatial and temporal relationships. We also need to develop new training algorithms that encourage the network to learn these kinds of representations. And crucially, we need to figure out how to evaluate whether the network is actually understanding these coordinate transformations or just memorizing them.
I'm still a believer in the power of deep learning, so I would focus on exploring ways to incorporate more structured data into the training process. Maybe that means using knowledge graphs to provide the network with explicit relationships between concepts, or using simulated environments to allow the network to actively explore and experiment. I also think we need to develop better ways to visualize and interpret the internal representations of deep learning models so that we can get a better understanding of what they're actually learning and how they're performing reasoning.
From my point of view, it all comes back to neuroscience. We need to study the brain more closely to understand how it performs reasoning, how it integrates different modes of representation, and how it learns to manipulate spatiotemporal relationships. I'm particularly interested in the role of temporal processing in reasoning. How does the brain encode and process time? And how can we incorporate these mechanisms into AI systems? I think that's a key area that's currently being overlooked. Perhaps leveraging the principles of hierarchical temporal memory could significantly improve the sequential optimization capabilities of language models.
Hierarchical temporal memory. That's Jeff Hawkins' work, right? On intelligence? I remember reading that years ago. Interesting to see that coming back around.
Yes, it's a very relevant area. Also, let's not forget about the common sense gap. Language models can generate impressive text, but often lack basic common sense knowledge. Integrating common sense knowledge bases with neural networks is a crucial step towards building more robust and reliable reasoning systems.
And that common sense knowledge, I think, is inherently tied to our understanding of the physical world, our ability to reason about objects, space, and time. It's not just about memorizing facts, it's about having a deep understanding of the underlying physics. And that's where the spatiotemporal piece comes back in again.
Yes, and I think a core question that we should be asking is, how can we design AI systems that are not just intelligent, but also explainable? If we can't understand how a system is making decisions, how can we trust it? That's why I think the less is more approach is so appealing. Simpler models are inherently more interpretable, and that's crucial for building AI systems that are safe and reliable.
Explainability is definitely a growing concern, especially as AI systems are being deployed in more and more critical applications. No one wants a black box making life-altering decisions.
Right. Imagine a self-driving car making a split-second decision in an emergency situation. We need to be able to understand why it made that decision so that we can learn from it and improve the system.
And that explainability, again, ties back to the underlying representation. If the system is using a clear and interpretable coordinate system, it's much easier to understand its reasoning process. If it's just a bunch of weights and biases in a deep neural network, it's practically impossible.
Okay, so if we are pushing this further, how do we think the Hegelian-inspired enhancement suggested in the original LIMO abstract will contribute to the development of more robust and nuanced solutions for sequential optimization? And can this potentially refine the brute force element of current deep learning techniques?
A Hegelian approach, with its emphasis on thesis, antithesis, and synthesis. Antithesis, a need for dialectical reasoning within the optimization process. Perhaps a crucial missing component of current models is the ability to synthesize contradictory data and insights. Traditional symbolic logic can model this more readily and elegantly than current deep learning systems.
That's interesting. I hadn't thought about it in those terms. So, you're saying that the system should be able to actively explore different perspectives and reconcile conflicting information?
Yeah, like translating between different frames of reference, different coordinate systems. That's essentially what dialectical reasoning is all about. It's about seeing the problem from multiple angles and finding a synthesis that incorporates the best aspects of each perspective. It requires a system capable of switching between different conceptual frameworks, and that's precisely what current deep learning models struggle with. They are more akin to static, data-driven algorithms.
And that dynamic switching between frameworks, that's where the temporal piece comes back in. It's not just about having different representations. It's about being able to transition smoothly between them to maintain coherence across different perspectives. Maybe the Hegelian process helps refine the representation over time so that fewer samples of data or less compute is needed. Maybe the model becomes more efficient by developing its representation more efficiently.
So, how would that actually work in practice? Are we talking about different neural networks that specialize in different perspectives, and then a higher level network that integrates their outputs? Or are we talking about a single network that can dynamically reconfigure itself to adopt different perspectives?
Potentially both. In neuro-symbolic systems, you could have symbolic modules explicitly representing different perspectives, and then neural networks that learn to map between them. The key is to have a clear and interpretable way to represent these perspectives and the relationships between them.
I lean toward the single network that can dynamically reconfigure itself, but with explicit constraints on how that reconfiguration can occur. Like, maybe the network has a set of internal maps or coordinate systems, and it can learn to activate different subsets of these maps depending on the context. That would allow it to switch between different perspectives without losing coherence.
And the learning process, I think, would need to be more interactive. Instead of just passively absorbing data, the system would actively explore different perspectives and receive feedback on its attempts to reconcile them. It's almost like a Socratic dialogue, where the system is constantly being challenged to defend its reasoning and refine its understanding.
That sounds incredibly complex. I'm not sure if we're even close to being able to build systems like that.
It is complex, but I think it's a necessary step if we want to move beyond simple pattern matching and build AI systems that can truly reason. The challenge is to find the right balance between complexity and simplicity, to identify the core principles that allow the brain to perform these kinds of computations efficiently.
And to understand how the brain translates between different coordinate systems. That, I think, is the key to unlocking true AGI. Once we can crack that nut, the rest will follow.
Agreed. And going back to the idea of less is more, it might not be as intuitive as simply scaling back model sizes. Instead, it might involve a focused effort to find the minimal set of neural structures and algorithms necessary to reproduce sophisticated reasoning. This is akin to finding the most parsimonious explanation in science, prioritizing simplicity without sacrificing explanatory power. This approach aligns closely with biological neural networks, which are often highly optimized for efficiency. The less is more philosophy could provide invaluable constraints for designing efficient and understandable AI systems by drawing inspiration from how biological brains solve complex problems with remarkable energy efficiency.
So, it's about efficiency, not just simplicity for simplicity's sake.
Exactly. And that efficiency comes from understanding the underlying structure of the problem and choosing the right representation and algorithm to solve it.
And from being able to translate between different coordinate systems.
And from studying the brain to understand how it all works.
Well, this has been a fascinating discussion. I'm still not entirely convinced that deep learning is a dead end, but I'm definitely more open to the idea that we need to explore alternative approaches, especially those inspired by neuroscience.
Agreed. I think the future of AI lies in a hybrid approach that combines the strengths of both neural networks and symbolic reasoning.
and in algorithms that can translate between different coordinate systems.
Absolutely. And to our listeners, thanks for joining us on this Cognitive Spirals episode as we delve into these fascinating and complex topics. If you have any thoughts or insights of your own, we'd love to hear from you. Until next time, keep exploring.